Before I begin talking about scalability, I thought I'll take some time to talk about software development in general because that is essentially what this talk is really about, right? Uh, so, I mean, if you look at, what a developer does every day in his life, you kind of see this cycle going, you know, I mean, definitely you can describe some processes, but if you ask a developer what he does the whole day, he'll say, I'll write some code and run it, and because I'm a human, I make mistakes, and I spend the entire day debugging them. Now, I'll take another detour for a second, and talk about, how people have tried to evolve software development over the years, and usually when people say, I'm gonna help developers, they talk about libraries, and this is kind of the vision they show you, is you usually have something like this, they say, okay, this is your piece of code right now, and right now you're using these many third-party libraries and frameworks, in some time I'll write some more libraries and frameworks, and this would look something like this, because over time the libraries will increase, and you just have to write this amount of code, and it's the ultimate software dream that you'll just have these components which you'll just have to fix together like a jigsaw puzzle, and your software will be complete in a second, And if this was true, none of us would be sitting here right now, because I mean, if the software could be completed in a second, why would you hire expensive engineers at Google to write it, right? So what actually happens is something like this. So the third-party libraries grow, but so does your code. So if you really think about it, take an example of, say, video games. Back in the day, you must have played something like Doom, and the guys who made Doom, it took them years, and right now, there are probably libraries out there, game libraries, that'll allow you to make something like that in probably a week or so, right? But the problem is nobody wants Doom anymore, right? They want Doom 4. And that's been in development for the past 5 years. And then when Doom 4 comes out, there'll be libraries to make that in a week. But nobody will want Doom 4, then the people want Doom 5, So it's the same thing. The third-party libraries and frameworks grow, but so does your code, So that's the libraries part, So coming back to that original cycle, that edit, run, debug cycle, And here again, it seems that people are mostly focusing on the edit part, I mean, when you talk to developers, you have these sort of religious talks about programming languages, right? And if you really think about it, like, does it really matter if you type int a is equal to 5 or a is equal to 5? Or you type like list or add, or use any of those to type the thing in, Or let's take a more complex example, like the for each loop in Java 5. Like, sure, you can say that, Java 5 is much more neater and cleaner, but like, did you reduce our software development time by 50% just because you used your for each loop? I mean, when was the last time you couldn't complete a software project because you couldn't type it in fast enough? I mean, did you hire somebody last week saying, this guy doesn't know a damn thing, but he can type really, really fast, It doesn't really happen, right? What happens is, I mean, you're all humans, right? So you write some code, and you run it, and you will make errors in it, We made all these frameworks and languages where we assume, that if you make an error, that's an exceptional condition, that's an error condition. And that's okay for a computer, right? For a computer, maybe that making an error is an exceptional condition. But if you're a human, errors are the default for you, right? I mean, most of the times you will make errors, and in an exceptional condition, the program will come out right. That's what happens, So if you kind of take the graph and, make the circles according to the amount of time taken in them, it'll look kind of something like this. And no, before you ask me, this graph is not drawn to scale, because if it were drawn to scale, you won't even see those edit and run circles over there. So now going back to the debug part, I mean, the way you debug hasn't really changed at all, like pretty much since the dawn of programming, right? And the way you debug is with the same model of breakpoints. Okay? And the thing about breakpoints are, the breakpoint model is broken. So consider something like this, on mouse move. This method is called, say, every time you draw a perfect S, which covers your entire screen, a perfect S, And once you draw that perfect S, your program crashes. So you take out your standard debugger and you try to debug it, and you place a breakpoint on it. But the first time you move your mouse, it breaks. So you never even reach the point where you make your perfect S. And then you try something like you try to put your hit counts, or you try to put some conditions, and the developer is drawing perfect S's on the screen the entire day, trying to see if it was the right condition, or the right hit count, and it's just so painful, So, and just this whole idea of you have to reproduce bugs in 2009, is such a huge pain, And for something like multi-threaded programs, it's impossible, right? You can't even reproduce them. And it is things like bugs which cause programs to fail. It's not typing which causes projects to fail, right? And it's even worse when if there's some code on your server which goes down, right? I mean, if it's something like Gmail or not Gmail, it's Google. So something like eBay or something goes down, it's even worse to debug it because you got to reproduce your entire production environment, and the site is down. It's your main source of revenue. It's just crazy. So if you really think about it, software development in the past 20 years hasn't really changed. I mean, in 2009, it is still okay for people to use VI or Emacs. And compare that to any other industry. Okay? I mean, have you ever seen a graphic artist say, Photoshop is too expensive, I'll just use MS Paint, It just never happens, right? So we got to change something, right? And how are we going to change it? Well, we're going to change it by using a very simple mechanism. We're just going to record every single thing that happens in your program. And by every single thing, I mean everything. Every method call, every variable that's assigned, every branch that's taken, everything that happens in a program. So what does that mean? I mean, it's cool you're recording, but what does that mean, right? I mean, well, it means you never, ever, ever have to draw that S again on your screen once it crashes, And as you'll see, as I'll show you now, the new debugger that I'm going to show you, it does not use breakpoints. You do not have to deal with breakpoints anymore. It's broken. Do not do it. And, I mean, it's obviously great for something like, if you have a problem in a production site, you don't have to reproduce your entire environment, and, your entire database, and try to reproduce your problem. Now, you may say, okay, recording is so cool, So why aren't other people doing it? Why don't we see a whole bunch of recording-related tools out there? Well, the reason is because it is really, really, really hard. I mean, think about it. Your CPU can execute millions and millions of instructions a second, And if you're going to record everything, and if you're not clever about it, either you'll run out of memory really, really fast, and even if you somehow circumvent that, your program will go so slow that it'll be unusable. And if you can't even use the program, I mean, what's the use of having the recorder running? So I'll show you, just to show you how tough this problem is to solve. I'll give you a little demo. So I cannot tell you the exact other tool that I'm using to compare against it because my lawyers have advised against it. But what I can tell you, you do a Google search and you'll probably come across it pretty fast. This is a tool that has been developed by a university and it's been in development since 2002. There's papers since 2002. And they have published papers at UPSLA, and they even had a demo at last year's Eclipse Con or something. So they're a pretty credible source. It's not just some 20-something-year-old guy sitting all alone in a room, doing some stuff, So over here you have this program, and it's a C compiler written in Java, and it takes this C file, something like this, and it converts it to LLVM. So I'm just going to run it normally so you can kind of get the feel of how fast this program actually runs. So I'll just run this normally right now, and you can see it just completes instantly. Oops. Just wrote the output instantly. Just convert it to LLVM. And now I'm going to run the same program with this other recording tool. And it's running, still running. It's still running. So it's taking a bit of time to run, you know. So I'll run my recorder while this recorder is still running. So that's what I'll do. So this ran with my recorder, and it just completed instantly. The other tool is still running, as you can see. So I'll do something else, you know. So this file I opened was, let's see, how big was it? You know, it was 69 lines long, right? So I'm gonna run this with, let's see, 1600 lines, you know, 10 times, over 10 times, I guess. 30 times, I guess, yeah. So the other program is still running, as you can see, and I'll run this on an even bigger file. And this is running on an even bigger file. And you can see it's completed, and the other program is still running. I'll actually stop this program because it doesn't complete even after half an hour, and I gave up after that. So you say, yeah, it's good to have a recording, you know, that's good, but what does that mean for me? I mean, you just, you know, adding more stuff to my program, making it slower. I mean, what's the use of this thing? So I'll show you the use of this thing. Let me close this down. So now I'm going to show you the time traveling debugger and how it works without breakpoints. Now I'll tell you, you know, like I've been researching this time travel thing for a while, but it's not been thoroughly researched. So, you know, keep your belongings, you know, keep hold of your belongings because you don't know what will happen. So this is a really small program, and it just prints out a bunch of stuff. You'll see. I'll just run it normally for a second over here. And you can see just completes instantly, it just prints out a bunch of lines. That's all it does. It does some comparison, and it calls this binary search method a few times. That's all it does. It's a pretty simple program. And now this is running in our Eclipse plugin. So near your run and debug buttons, we now have the record button. So now I'm going to launch this program with recording enabled. So I ran this program and it completed. It produced your output. And now that recording has been saved to a single file. And I can share that file among any number of developers, and they can take a look at it and run it in a debugger. No need to replay the program. So I'll share the debugger now. So now I'm running the debugger off the recording. And as you can see, just like your normal program, right, I can see my stack trace, and I can see my local variables over here. And like your normal debugger, I can step forward in time. I can see the variables changing. But unlike your normal debugger, I can also step back in time. You know, I can see the variables changing back. You know, and you say, oh, that's time travel because I can travel back in time. You know, but no. To make full use of this recording, you have to reinvent the debugger. So how are you going to reinvent the debugger? Well, first off, this whole stepping thing. You know, I mean, why step at all? I mean, if you look at this, you see this green line? It shows you the execution path of this call to this method, only for this call. And instead of stepping, you know, I can just click on this line, and I can step anywhere I want. You know, I don't have to step one by one, and you can see the state changes. Yeah, you know, so I'm stepping one by one. I can step anywhere I want. I don't have to look through it, and I can instantly see, you know, this if statement was taken, this else statement was not taken. I don't have to step through the entire method to see which statements were executed or not. And that's good, you know. You say, oh, that's awesome, you know. But what about this loop, Prashant? I mean, you have this loop from 1 to 10, and you know, I mean, how do I step back and forward in this, right? So that's a huge problem. Do I still have to use my normal stepping methods? And again, in this loop could be from like a 1 to million, right? And in a normal breakpoint-based debugger, you can't really place a breakpoint on, you know, when the bug occurs. So the way we're going to tackle this problem is, since this loop iterates on I, I'm just going to click on I, and it shows me all the values that were ever assigned to I, the thread that assigned it, and the time at which it was assigned. Now time in this case is an event counter. So every event that happens in a thread happens at a particular time value that the debugger assigns to you. So now instead of stepping through this loop, I can actually just click on any of the values. And it just jumps to that point in time. You see IS3 now. I can click on any other value. It just jumps to that point in time. Yes? What does time mean? So time is a counter. So every event that is recorded in your program is assigned a time value. So that's what time means. So it just gives you an idea of what happened before what. So if you're debugging race conditions, you can see the time values. You can see where the race condition occurred. So so I can click on any value, and from there on, from that point in time, I can step forward or step backward. Now that's good. That's great. But you have this line over here. You have this line which has this nested method call. And this could be like a really arbitrary nesting, okay? Or it could be a chain method call like result.result.result.result. And it's a pain to use the normal step-in function to step inside these calls, because maybe you want to step on the third call on this line, but you press the step-in button and it steps in the first call to that line, and you want to see the return values and the arguments to that method, and it's just a pain to, see it on a normal debugger. So for that, we have a special view. We have this view called calls on current line. And it shows you all the calls on this line at this point in time. So it shows you these are the two calls, and I can expand it. I can see what the argument was, and I can see what the return value was instantly. And if I want to step into any call, I can just click on that call, and I can step on exactly that call. So that's good, but you say, I think there was some problem in this binary search method, right? And, I don't want to step all the way through it, So how am I going to get to there, In a normal debugger, I would just place a breakpoint and I'll just get break on that. So how are we going to use this without a breakpoint? Well, you can just right-click on that method and say run to method. And it just runs to the next call to that method. And again, you can see instantly, what the execution path to this call was. But then you say, you know what, Prashant? There may be like 1 million calls to this method. And how many times am I going to press run to method, right? I mean, how many times are you going to do that? So why not see all the calls to this method, Why not see all the calls? So this tree shows all the calls to this method. It shows you the return value, the arguments, the thread, and the time at which it was called, And I can just click on any method call, and I'll just jump to that call itself. And you can see the execution path changing as I changed the call. But then you may say, Prashant, this list can be really, really long. If this is like 1 million calls, you expect me to click on each one of them and see which one it was? Well, so you need some way to filter this, right? So let's say I want, all calls which reach this line which I'm just placing my cursor on. So I just put my cursor on that line and I say filter by line. And it just shows me all calls which reach that line. You can see all these calls reach that line. And again, you can filter by many other ways. You can filter by return value, or the calling object or the thread. And you can combine these filters in any way you want. And that's good, But you see, what? This program produced some output on the console, And this program is not running anymore. But I want to see what the output was. Maybe that output was something important. And I can't see that anymore. So why should I use a debugger? Well, you can see that output. So I'm going to open this view. It's called the recorded console. And it shows me what was output on the console. And that's good, that's good. But what you can actually click on any of these lines of output. And it jumps to the point in time at which that output was produced. So I can click on 3 and it jumps to the point in time at which 3 was output. So, you say that's good, but all this time travel is making me crazy. I mean, in my normal debugger, I just step forward and I know where I am. Okay, but all this time travel, I don't know where I am in time now. I need some way to figure this out. So, to keep you from getting lost in time, I had to put in some mechanisms in the debugger. So the first of those mechanisms is the back and forward buttons. Oops. And these are like the back and forward buttons in your browser. But they keep track of the last 10 calls that you stepped to. So these are the same methods, but different calls to these methods that you were in. And that's just a preliminary way of going back and forward, and just kind of keeping track. But a more elaborate way is the timeline view. The timeline view shows you the exact time you are at right now. And this progress bar shows you where kind of in the execution of the program are you, like how far are you down the whole execution of the program. So if I step out and let's say I step, to the beginning of this method, it shows me, okay, you're kind of in the beginning of this execution of the program, Or I can step, till the end, it shows, okay, you're pretty much, till the end. And you can do some other things, like you can place what are called time bookmarks, okay. These are bookmarks in time. So you can place them on the same line and the same file and the same call, but at different points in time. And anytime you can just jump back to those points in time. And you can obviously export these and put comments on these and share them among other developers and say, take a look at this point in time, something is happening. So that's the debugger, But this is a pretty small recording, and you're probably thinking, show me something bigger than this, So I'll show you something bigger. Now, I'm going to open a recording of the Antler parser generator. And you can see this is a 100 MB recording. And I'm going to just open this from the files itself. So you can see I'm not running this at all. I'm just opening it from these files. Just taking a bit of time, and yeah, it opens. And you can see just, I can just debug Antler, just as I normally would. And now, if you're not the creator of Antler, if your name is not Terence Parr, and I asked you, why was this line output? Was there a bug in Antler? It'll probably take you like the entire day to figure out with a normal debugger. But with this, you just click on this line of code, and it just jumps to that point in time. And you can see the entire stack trace. You can see the entire stack trace, and let's click on this line, and you can see the entire stack trace, and go back and see why the error occurred. So that's the debugger, but you're probably thinking, we are a web company. I mean, we are Google, okay, and you're showing me all these desktop apps. So I'm going to show you a web app now. So this is Jira, and you might have probably used it. This is a pretty common, popular bug tracking tool. And I'm just going to start it up now. Now, I'm doing something unusual here. I'm not starting this program with recording. I'm starting this program as normally as any of you would, No extra arguments on the command line, just out of the box installation. I'm just starting it up normally. And you can see I can browse it over here. And it's just running normally, right? So I'm going to do something over here. That was the other one that crashed. That was not our stuff that crashed, by the way. So I'm just going to attach a recorder dynamically to this running program. So you can see Jira running over here. And in this tool, I'm going to select the process for Jira, which is this one. And I'm just going to attach the debugger to it, the recorder to it normally. So now it's attaching itself to it dynamically, without any arguments, just out of the box installation. The program is still running. You can still use the program. So it's instrumenting all the classes, and doing all the stuff to have the recorder run. So it's going to take a little bit of time. And again, my program is fully usable at this point in time. There may be a little bit of wait because the class you're using may be being loaded, but you can see the loading is still being done and the program is still running. So now the recorder has completely attached itself to your program. And I can still use the program, If you see pretty much no change in performance, it's not taking an hour to get the same request, it's taking the same amount of time, It's running normally as you would expect it to run, So now I can also dynamically detach it. So I dynamically attach the recorder, and now I'm dynamically detaching the recorder. So now it's doing the whole detaching part. and you can see it produced a single file over here, 35 MB. And again, I can share this file among developers, and if you're Atlassian, you can debug this if you want. We don't have the source code to do that, so we can't do that right now. So, just to tell you some things about the recorder itself. The recorder is completely platform independent. You can run it on any OS you want, where you can run Java, and you can replay the recordings on any other OS. So you can take a Linux recording, play it on the Windows PC or Mac. JVM independent. We don't have any dependencies on the Sun JVM or any other JVM. And you can record any Java program. Okay? As long as it is Java, you can record. There are no issues. You can record whatever you want. OpenGL program, web app, anything. Now, I'm going to talk a little bit about some of the approaches taken by some of the other commercial tools out there and how we kind of differ from them. So, what some of the other tools out there do? I mean, we actually record the entire program. Every single statement that your program executes, every single thing it does. But what some of the other solutions out there do is they do something like this. So this is your program running in a straight line. Think of it as running in a straight line in time. And they say, you know what, recording everything is going to be too expensive. It's going to be too slow. So what we're going to do is we're going to record at certain intervals. So they record as each of those intervals. They capture the full state. Now, when you do a replay from those programs, I mean, first off, they are platform dependent because they can only run, most of the times they can only run a Windows recording on a Windows platform. So they will just play back your program from any of those checkpoints. And they'll play it back in a normal debugger, none of that fancy stuff that I showed you. Now, the whole problem with this, with the playback mechanism is, what if between one of these intervals, your program calls something like get time, or it just queries the external state, right? And it may be that when you're replaying the program, that external state is different. So what they have to do is they actually have to write wrapper calls to, all the APIs that query external state. So they actually can record only a certain type of application. So when you get one of these other applications, they'll say you can record only, say, Tomcat using these and these libraries. And if you use any other thing, we can record it for you. This is not the case with us. We can record anything that you want. Now, the recorder works on a sort of a whitelist model. So by default, we don't record anything. And you kind of give us in a config file what you want to record. So the reason why this model is there is because something like, let's say, you are writing your program. You probably do not care what is happening inside the Java libraries. Like, you don't really care, what happens inside Java not lang. Or if you're using Hibernate or Tomcat, you don't really care what happens inside Tomcat, And a lot of times, some of these third-party libraries, even if there's a bug in them, I mean, you didn't write it. You cannot debug it. And you probably don't even have the source for it. So all those libraries, they run without recording. And you just record what is your source code. So you just say, I'm just include com.google.** and only your code is recorded then. And that's the way it kind of works. But there's no limit. You can record anything you want. We don't place any limit on what you can or cannot record. It's just your choice. If you want the recorder to run extra fast, you can keep excluding stuff. Now, as far as the performance of the recorder goes, there are three kind of applications where we categorize, at least for performance. And the first is command line apps. So if you have something like a compiler, or some other command line tool. Now, since you're running it on the command line, you don't really care whether it completes in 1 second or 3 seconds, right? Because you're not really interacting with it that much. So these kind of apps, even if you're a little slow, it's kind of okay, And then you have the web apps. And again, in a web app, if you click on a link and it reaches you maybe 15 milliseconds late, that's fine. You expect that. It's a web app, The worst case are desktop apps, something like Eclipse, because you click a button and you want that instant, instant response. And if you don't get that instant response, then the program just becomes unusable, right? I mean, if you press Control Space in Eclipse, you expect the pop-up to come instantly. If it comes after a minute, that's useless for you. So that's how we kind of categorize performance. And now the recorder is kind of built to be scalable. So here's how it kind of works. You have your recorded threads, which are generating data in memory. And they're using some of your cores. Now, the recorder has these things called the load manager threads. And what these threads do is they capture all the memory that's being generated so fast, they compress it, they process it, and they save it on a disk or through a network. So if you think, I mean, this is mainly a problem of, how you're going to minimize that memory that's being generated so fast. So if you think you're running out of memory, you can either add more cores, so the load manager threads will be able to process it faster, or you can just add more memory. Memory is cheap. Or if you think your disk is too slow, you can have a RAID, you can have parallel disks to get that right speed. Or if you want, you can send the output to a network. You can attach multiple Ethernet cards and send the output through a network. Another problem that you may think you will face is GC pause times, because it is not uncommon to run into 1 gig or 2 gigs of heap sizes with this. But you'll see GC pause times are not an issue with this. Even if you have a 2 gig heap, you'll see it sometimes just instantly comes to 300 MB as soon as it's cleared. The reason for that is because we do custom memory management, So we don't really have that many pointers in memory, and the garbage collector works only in memory. The last point is the amount of execution recorded. So if you think, you have added enough cores, you're taking care of the memory, you've added your disk, but your program is still, not up to the speed, well, then you just have to exclude stuff. Most of the times you'll see, in a program, there's just maybe one class that's doing a lot of work, but you don't really need to record it. And you can just exclude it, and then the recorder will run to normal speed. So that is it for today's presentation. And if you're interested in this tool, you can actually go to our site and put your email address in there, and we'll send you a notification. However, there's one more thing. Now, I told you that the worst case for the recorder is when you're running a desktop app like Eclipse, because you want that instant response, right? You want that instant response. If you don't get that instant response, then it's unusable. Well, as it turns out, when I was showing you the debugger demo, that was being recorded. You just never notice it. And this is the trace file that it produced. Thank you.
So how big do those files get? That one's 184 megabytes, I see. And how fast?
How big those files get?
And how fast do they fill up? I mean, yeah.
Well, again, that's a really tough question to answer, because it is really dependent on the program. So again, something like Eclipse, you can see, I mean, we ran it for about 20 minutes or something, or maybe 10 minutes or something, I don't know. But it produced about 180, But there are some other programs out there, like something like JTrack. We see it's a small bug tracking tool like Jira. And even if you run it for 20 minutes or half an hour, it doesn't even produce a file that's 10 MB in size. But something like Jira can instantly produce tens of megabytes. So it is really, really dependent on the program. But what you can kind of get an idea from looking at it is, we're not generating gigabytes and gigabytes of file sizes. The file sizes are still in MBs, not in gigabytes.
Well, I mean, I'm not sure I'm not sure that that's true. I mean, this is MBs, but you've been running it for 20 minutes, and if you have a server,
yeah, of course. I mean, that file is going to grow. Yeah,
you're running it for,
of course.
For months.
So I mean, we are looking at.
And Jira, you said it produces a lot of.
So of course, so we're not saying it's not going to take space. It's definitely going to take space. The more you record, the more space. So again, you got to think of it as a cost-benefit thing. And of course we are looking at other solutions, right? You want to have maybe rolling logs, something like, keep this log on the disk only if a certain condition occurred or a certain exception occurred. Otherwise, just throw the recording away. So there are some of the solutions that we are looking at. But of course, I mean, if you want to keep everything, then of course you have to provide storage for it. But then again, you got to look at the cost-benefit ratio of it.
So Andrew Koh's Y-line system from CMU used a similar tracing kind of mechanism for debugging, but he had a very different interface for debugging, that rather than trying to stay at the code level, his philosophy was completely that what programmers wanted was understanding why a value was that way, where it came from. And he considered that to be one of the key questions that most people ask when they were actually looking at debugging. Is there a reason that you went with the text-based, source code-based approach for debugging, and could you actually go to a Y-line-based system, or do you think there's things that would keep that from working in practice?
I don't exactly get the other approach that you're talking about.
Sorry.
I don't exactly get the other approach that you're talking about.
So what Y-line did was...
Y-line?
W-H-Y-L-I-N-E.
Okay.
So Andrew Koh, who was at CMU working with Brad Myers, he's now at the University of Washington. So his system didn't really show, I mean, it showed you source lines, but he said that based on research that he'd done on how people debugged, that what people really wanted was, why does this variable have that value? Why is this part of the screen blue? And so everything he was doing was focused on that, not trying to imitate a old-fashioned debugger with the forward and back necessarily. And I was curious if there were reasons why you stayed with a debugger-like view and didn't go to something more ambitious, whether there's technical reasons why you can't do that in practice for something that's going to be industrial strength.
Well, I mean, technically, we have all the recorded data, so we are actually just viewing the data in a debugger. So if you want, you can pretty much hack and slice it in whatever way we want. The way we currently have a mechanism, for figuring out why a value occurred is really just to look at that value and click on it in the variable history view and just go back to that point in time. And again, this is a matter of debate, right? Some people just want that other kind of debugger that you described, and some people probably would like this debugger. So it's really not I can't really give an objective answer to that because it's a matter of preference, right? This is the approach that we think most people will like, and if developers come and say to us, you should try this other approach, then maybe we look at some other approach,
You could very easily imagine integrating that sort of approach into what you've got, I think. Did you show us anything where you looked at multiple threads? And the other question I have is, do you store I/O events? Like if I read in a gigabyte of data, what happens to that data? Right?
Well, so two questions, right?
Yeah.
So first off, about multiple threads. Now, the recorder is completely meant to support multiple threads. The demo does not actually show multiple threads running, but the recorder is completely aware of it. You saw there was a thread number over there. That was a recorder assigned thread number. The debugger is not fully complete yet, but you can actually when the final release is done, you can actually click on that thread number and it'll show you all the system assigned ID and what the exact name and priority of the thread was.
But you have the forward and backward notion, and does that skip around between threads? That
Well,
kind
when
of
you do it,
I wasn't sure exactly.
when you do the back and forward in the stack trace, you will see what the exact stack trace of all the threads was.
Oh, I see.
So you'll be able to look at the stack trace and pick your thread and go forward with it. Yeah. And what was the second? The second question was about I/O.
Yeah, if you're reading in a whole bunch of I/O, do you actually store
So
that?
if you're reading in a whole bunch of I/O, now again the recorder just looks at the bytecode level. So if you're reading in a huge byte array, it'll record that byte array and save it. So that's how it kind of also works with third-party libraries. If I was not too clear about that. So if you do not record a third-party library, or if you have something like file.read, the recorder will store the argument to that call, file.read, and it'll store the return value of that call, which is what you want when you're debugging it. Is you want to know what went inside and what came out, because the library probably is just a black box for you.
But it also stores the data compressed.
Uh-huh.
It stores it in compressed fashion as well.
Yeah, it is in compressed fashion. So yeah, I mean, it won't be reflected in your trace.db that you.
Basically use extra cores to
Yes, the load manager threads they take care of compressing all that data. Any other questions?
So this is not actually a question. It's not anything about debuggers, but I was very amused to note in your binary search that I think it has the bug that every published binary search has, which is that you, in which
Binary searching over 10x.
I copied the algorithm from Wikipedia.
that that so
Yes.
So Josh has blogged about that bug, and I've actually fixed that bug in the JDK, where you have the
Well, what is that? What is
the
that?
overflow. When you take the midpoints of two positive numbers, you if you're really careful, you worry about negative overflow.
Okay.
So it's not a very important bug, but it is a famous one.
But it was a fixed length, 10 length array, like kind of array, right? So that can't happen.
Well.
It's really fixed length. It wasn't. You were binary searching over. Show us your function.
Okay, I'll show you the function. Okay, let's see. Where is the?
I thought it was just an array of length 10 with 10
Oh
elements.
yeah.
Oh, so if it's hard coded, then
Yeah, I think it was hard coded.
Yeah.
See,
well.
Only at Google can you get such.
All right.
First time we've seen that. See, I told you. See, you need a debugger to find the answer. This one's mine. Oh, yes. Oh, cool.
Yeah.
Just replace the slash.
Anything else?
We're good to go.
No?
Triple.
Okay. Thanks a lot, Prashant. That was
Thank
great.